Ever notice how sometimes the simplest solution, well, it isn't always the best? Like,
No.
imagine you have a splitting headache. You could just wait for it to pass, or you could take an aspirin.
Right.
Aspirin's obviously more complex, right, with all its interactions in the body, but it's also way more likely to actually get rid of your headache. Today, we're diving into a really interesting area, the world of scientific models, and we're going to challenge the assumption that simpler is always better.
It's an assumption most of us make without even thinking about it.
It really is. We'll be looking at a 2025 paper called "Is Occam's Razor Losing Its Edge? New Perspectives on the Principle of Model Parsimony." It's by Dubova and some colleagues. Occam's razor, of course, is that old idea that the simplest explanation is usually the best.
Right. The classic example is if you hear hoofbeats, think horses, not zebras.
Exactly. By the end of this deep dive, you'll understand what model parsimony really means. We'll also talk about when it's useful and, crucially, when it might actually hold us back.
Sounds good. I'm ready to have my assumptions challenged.
Let's start by unpacking this idea of parsimony itself. The paper breaks it down into two main types, and I think that's really crucial for this whole debate.
Yeah, I can see how that would be important. So what are these two types?
The first type is parsimony by constraints, which refers to a model's flexibility. So a highly constrained model is very rigid. It can't easily adapt to new data, while a less constrained model is more flexible.
Makes sense. So like a highly constrained model is kind of like a fixed gear bike.
Exactly.
It's efficient for specific situations, but not very adaptable.
Yeah, if you hit some rough terrain, you're in trouble.
You are. And then a less constrained model would be more like a mountain bike.
I like it.
With all its gears and suspension, it can handle a much wider range of situations.
Exactly. Now, the second type of parsimony that they talk about is parsimony by components. And that's all about how many elements a model has. So things like variables, causes, and underlying mechanisms.
I see. So a model with fewer components would be considered more parsimonious by component.
Exactly. A great example of parsimony by components is Noam Chomsky's theory of language.
Chomsky. He's famous for that.
He proposed a small set of universal grammar rules to explain how all human languages work.
Right. He was looking for that underlying structure that connects all languages.
Exactly. On the other hand, we have these huge language models that are used in AI, and these are not parsimonious at all. They gobble up massive amounts of data without starting with any strong assumptions about language structure.
And yet they're both giving us some really interesting insights into how language works.
It's true, and it really highlights something that the paper makes a big deal about. Parsimony doesn't actually guarantee accuracy.
So simpler isn't always better.
Not necessarily. Sometimes adding complexity can actually improve a model's predictive power.
Okay, I can see that. Especially when those additions reflect, real-world nuances.
Exactly. It's kind of like the aspirin versus the untested drug example we were talking about earlier.
Right, with a new drug starting with the assumption of no effect is the safest bet.
Exactly. But aspirin's complex interactions with the body are really well known.
Yeah, so a model that accounts for those interactions is going to be much more accurate.
Exactly. A simple model might miss some crucial side effects.
That makes sense. And there's also this double descent phenomenon that the paper talks about,
Right.
which actually challenges the traditional bias-variance trade-off.
Can you unpack that a little bit?
Sure. So the classic view is that as models get more complex with tons of parameters, they overfit the data, and then they predict poorly on new data.
So it's like they're memorizing the training data instead of actually learning the underlying patterns.
Yeah, exactly. But it turns out that some extremely complex models, even with more parameters than data points, can be incredibly accurate.
So they're not overfitting like we thought they would.
It seems that way.
Yeah.
It's like they're uncovering these hidden patterns that simpler models just can't detect.
So more is more in this case.
Sometimes, yeah. Which raises another interesting question about interpretability.
Right. Just because a model makes good predictions doesn't mean that we understand why.
Exactly. There's a difference between understanding how the model works internally, that's intrinsic interpretability, and extracting meaningful insights about the real world from its external interpretability.
So a model could be a black box internally,
Right.
but still give us useful information about the world.
Exactly. And the paper gives this really interesting example of economists misinterpreting a simple regression model.
So even with a simple model, we can fool ourselves into thinking we understand when we really don't.
It happens more often than you'd think. A model can be simple, but if that simplicity doesn't reflect the real world, it can lead to incorrect conclusions.
It's like using a map that only shows major highways to navigate a city full of back streets and alleys. You might think you know the way, but you're going to get lost.
Exactly. So parsimony in itself isn't the be-all and end-all.
It's a tool, and like any tool, it has its uses and its limitations. So should we just ditch it altogether then?
Well, not necessarily. It can still guide research, but we need to be aware of the potential pitfalls.
I see where you're going with this. So a highly parsimonious model might actually lead to overly simplistic experiments.
Right, if we're not careful.
Can you give us an example of that?
Sure. The paper highlights a tendency in fields like psychology to break down complex phenomena like memory or attention into these isolated, overly simplified models.
So we're trying to understand the human mind by taking it apart piece by piece.
Yeah, and that can obscure the bigger picture of how these things actually interact.
It's like trying to understand a car by only looking at the engine.
Right, you're missing all the other parts that make it work.
So we need to be careful about oversimplifying things. But what's the alternative?
Well, there's this intriguing finding that sometimes random experimentation actually leads to better models than those driven by theory.
Wait, you mean just experimenting without a rigid theoretical framework?
Yeah, sometimes it can yield better results, especially when our theories are based on overly simplistic assumptions.
So when we're studying complex phenomena, maybe starting with a complex model is actually the more sensible approach.
Yeah, one that embraces the messiness.
Okay, so where does that leave us? Is it complex, good, simple, bad? It feels like we're going back and forth.
It's definitely not that black and white. It's about choosing the right tool for the job. And parsimony is just one tool in our scientific toolbox.
Okay, so we need to be more nuanced in how we think about parsimony. It's not a magic bullet.
Exactly.
All right, we've talked about accuracy and interpretability in research, but what about resource efficiency? Aren't simpler models usually more efficient in terms of computing power and time?
That's a conventional wisdom. However, remember the double descent phenomenon we were talking about?
Yeah.
Sometimes adding complexity can actually speed things up.
Now that is counterintuitive. How does that work?
There are these emerging techniques where you can use a complex model to emulate a slower, more parsimonious one.
So it's like building a powerful engine and then using it to do the work of a simpler one, but much faster.
Precisely. So you get the best of both worlds, the accuracy of the complex model and the speed of the simple one.
So you're saying that parsimony isn't always the answer when it comes to resource efficiency either.
Right. It's not as simple as we might think. And the same applies to dealing with limited or noisy data.
Which, let's face it, is a pretty common challenge in science.
It is. Traditionally, parsimony was seen as essential in these situations to avoid overfitting.
Right. The idea was to keep things simple so you wouldn't read too much into the noise.
Exactly. But the paper challenges that view as well.
Really? So what's the alternative?
Well, those super complex models we talked about can sometimes actually extract real signals, even from messy data.
So even with limited or unreliable data, these complex models can still uncover meaningful patterns.
Yeah, in some cases they can. And then there's also the idea of model ensembles, where you use multiple complex models together to account for uncertainty rather than trying to find one true model.
So instead of putting all our eggs in one basket, we spread the risk across multiple models.
Exactly. It acknowledges the inherent complexity of the world and that our models are always going to be imperfect reflections of that complexity.
That's a really interesting way to think about it. So we've covered a lot of ground here, but there's one final piece of the puzzle that I think we need to discuss. The paper discusses what it calls the belief in a parsimonious world.
Okay. You mean like the assumption that the universe is inherently simple at its core?
Exactly. Some scientists fundamentally believe that the phenomena they study are governed by a small set of elegant rules.
Right. They're looking for that underlying simplicity.
Yeah. The paper even cites Copernicus as an example. He used parsimony to argue for the heliocentric model of the solar system.
Because it was a simpler explanation than the Earth-centered model.
Exactly. But the paper challenges this assumption.
Okay, so they're saying that maybe the universe isn't as simple and elegant as we'd like to believe.
Yeah, they point out that many fields from psychology and climate science to even physics are starting to recognize that complexity is often inherent to the world we study.
That's a pretty profound idea. So where does that leave us with Occam's razor then? Is it completely irrelevant?
Not necessarily. Remember, it's a tool, and like any tool, it has its place.
I see. So it's not inherently good or bad. It depends on the context, the goals, and even the beliefs of the scientists involved.
Exactly. But the paper doesn't just leave us with that, does it? It proposes a new way of thinking about all of this.
Oh, really? Now I'm really curious. What is it?
They suggest a new approach. Start with complex models to explore the data, and then distill those models down to simpler, more interpretable versions for practical use.
So embrace the complexity initially to explore the data landscape, and then simplify to explain and apply the findings.
You got it. It's a fascinating idea, and it raises a big question. How might this approach change the way we learn and understand things in our own lives?
That is a really interesting question to ponder. It's amazing how much our understanding of model complexity has changed in just a few years. This idea of starting with a complex model and simplifying it is almost like turning Occam's razor upside down.
Instead of shaving things down right away, we're letting the complexity grow to see what we can learn.
Exactly. And the paper talks about some really interesting techniques that make this possible.
Okay, like what?
Like distilled learning and sparse approximators.
Okay, those do sound pretty sci-fi.
They kind of are,
Yeah.
but they're also very real and very powerful.
So can you break those down for us?
Sure. So imagine you've trained a really complex model, something that can process tons of data and find those subtle hidden patterns. But this model is a total mess. It's hard to understand and even harder to explain to others.
It's like a brilliant but eccentric scientist
Exactly.
who can solve any problem, but nobody knows how they do it.
And that's where distilled learning comes in. It's like taking all that knowledge and distilling it into a clear, concise textbook.
So anyone can understand it.
Exactly. We essentially train a simpler model to mimic the behavior of that complex one. We use the output of the complex model as a teaching tool for the simpler model.
So it's like the student surpassing the master.
Yeah, in a way, but benefits everyone.
I like it. And what about those sparse approximators?
So picture a massive neural network with millions of connections. A sparse approximator is like going through that network and snipping away all the unnecessary connections.
So we're decluttering the model to find a simpler, more efficient way to represent that same knowledge.
Exactly. And it's interesting because the paper actually suggests that these techniques, distilled learning and sparse approximation, are sometimes more effective. It seems counterintuitive, but starting with complexity can actually be a shortcut to a good, simple model.
So sometimes you need to go big to go small.
You got it. It's like exploring a vast forest before figuring out the most efficient path.
This is blowing my mind. I mean, this has some pretty big implications for how we learn and understand the world.
It definitely does. We're always trying to simplify things to make sense of all the information coming at us.
But maybe we shouldn't be so quick to jump to those simple explanations.
Right. What if there's more to the story?
Yeah, what if we're missing something important by oversimplifying?
That's a great point. The paper suggests that embracing complexity, at least at first, can lead to a much deeper and more robust understanding in the long run.
So instead of reducing everything to a soundbite, we should be willing to grapple with the messiness, the nuances.
Exactly. Don't shy away from complexity. Explore the different sides of a problem. You might be surprised by what you find.
Okay, I'm definitely on board with embracing complexity. But how do we actually do that in our daily lives?
Well, that's a great question, and there's no easy answer. It's something we each have to figure out based on our own goals and situations.
But this whole discussion is encouraging us to be more mindful about how we approach learning and understanding.
Exactly. It's about cultivating a mindset that's open to complexity and embraces uncertainty.
So it's not so much about following a set of rules, but about developing a certain way of thinking.
Right. A way of thinking that sees simplicity not as a starting point, but as the goal.
Embrace the mess, then find the elegance within it. And that brings me to a question I've been thinking about. Part of me still really appreciates a simple, elegant explanation.
Of course, simplicity has its appeal.
It just feels so satisfying.
It can be aesthetically pleasing, intellectually stimulating, and even practical. You wouldn't use a complex neural network to write your grocery list.
No, definitely not. There's a time and a place for both simplicity and complexity.
Exactly. The key is knowing when to use each one.
Finding the right balance between the two.
Exactly. The yin and yang of knowledge.
So embrace complexity, seek simplicity, and find the balance. I'm feeling much better about this now. This paper has given us a lot to think about.
It has, and there's still more to come.
Really? What else is there?
Well, the paper also gives some really interesting examples of how this whole debate is playing out in different fields.
Oh, wow. So it's not just theoretical.
No, it has real-world implications.
I knew it. Okay, so give us some examples. What fields are wrestling with this?
Psychology is a good example. There's a growing realization that a lot of the traditional models of human behavior are too simple. They often ignore things like social influences, cultural norms, individual differences.
So we've been trying to understand the human mind without considering the context it actually operates in.
Exactly. And that's led to some pretty misleading conclusions.
So we need to embrace more complex models that can account for that inherent complexity of human behavior. What about other fields?
Climate science is another good one. Early climate models were relatively simple, but they weren't very accurate.
Because they couldn't capture all the interactions between the atmosphere, the oceans, the land, and human activity.
Precisely. But as scientists have developed more complex models that take all those things into account, the accuracy has improved dramatically.
So psychology and climate science are leaning towards complexity.
It seems that way. But what about physics?
Yeah, physics has always been about finding those elegant, unifying theories.
And the paper actually addresses this directly. It acknowledges that physics has a long history of finding simple, elegant explanations for the universe.
Like Newton's laws of motion and Einstein's theory of relativity.
Exactly. But it also points out that even in physics, there are areas where complexity is starting to become unavoidable.
Really? Where's complexity winning in physics?
Or quantum mechanics, for example. It's incredibly complex, and we're still trying to figure out how it all works.
So even in physics, those simple, elegant explanations might not be enough.
Right. Maybe complexity is just the nature of reality. The deeper we go, the more complex things become.
That's a really interesting thought. So maybe Occam's razor isn't so much dull as it is evolving.
The razor is being sharpened by the very complexity it's trying to cut through.
That's a great way to put it. But I have a feeling this whole debate is far from over.
I agree. It's a fundamental question about how we understand the world, and it's going to keep evolving as our knowledge and tools do.
Okay, so we've talked a lot about parsimony and complexity, and it seems like parsimony, that preference for simple explanations, isn't going away.
It's definitely still relevant.
But it's definitely evolving.
Yeah, in light of all this new research on complexity.
It's like we're constantly refining our tools for understanding the world.
That's a great way to put it. And the exciting thing is that this isn't just some abstract theoretical debate. It has real implications for how we do science, how we build technology, even how we make decisions in our daily lives.
Exactly. So let's dive into those implications. Starting with science. We've touched on how different fields are grappling with this whole complexity issue. But what does this shift really mean for the future of scientific discovery?
Well, for one thing, it might mean we need to rethink our traditional approach to experimentation. If we're studying a complex phenomenon, designing experiments based on a simple model might not be the best way to get to the truth.
So instead of trying to control for every possible factor, we might benefit from a more exploratory approach.
Exactly. The paper talks about how random experimentation can sometimes lead to more robust models than those that are based on theory.
So it's about being open to unexpected discoveries.
Right. Science is about exploration after all.
That's true. But that's a pretty big shift from how science has traditionally been done.
It is. But science has always been about challenging assumptions and pushing the boundaries of knowledge.
Yeah, and sometimes that means embracing new ways of thinking and doing. Okay, so that's science. What about technology? How does this whole parsimony versus complexity thing play out in the world of AI and machine learning?
Well, we're already seeing it with the rise of those huge language models and other complex AI systems.
Right.
They can do some pretty incredible things.
Yeah, they're really pushing the limits.
But they're also incredibly complex.
Which raises a lot of questions about interpretability bias, even safety.
Exactly. How do we make sure these powerful tools are being used responsibly?
That's a big one.
Yeah.
And that's where those techniques we talked about earlier come in.
Right, distilled learning and sparse approximation.
They offer a way to harness the power of complexity while still maintaining some degree of control and understanding. It's like we're trying to tame a wild animal.
In a way, but it's not just about taming it, it's about understanding it.
Right. These AI systems are like alien intelligence.
Yeah. Right, and we're still trying to figure out how they work.
Which brings us to maybe the most important question of all. What does all of this mean for us as individuals?
I think it challenges us to be more humble about what we know and what we think we understand. We often want simple explanations and easy answers.
Yeah, the world is messy and complicated.
And we need to be okay with that.
So instead of trying to oversimplify everything, maybe we need to embrace that complexity.
Don't be afraid to ask questions, to challenge your own assumptions, to dig into the details.
The more comfortable we are with complexity, the better equipped we'll be to make sense of the world.
I agree. It's about expanding our capacity for understanding.
And hopefully making better decisions along the way. So embracing complexity is important. But how do we do that without getting totally overwhelmed?
That's where that balance comes in again. It's not about choosing complexity over simplicity. It's about knowing when to focus on the big picture and when to zoom in on the details.
It's like being able to see both the forest and the trees. Those are some powerful takeaways.
And they reflect a much broader shift that's happening in science, technology, and culture.
It's like we're moving away from that reductionist view of the world.
Yeah, that everything can be broken down into simple parts.
Like towards a more holistic, interconnected understanding.
Exactly.
It feels like we're entering a whole new era of knowledge.
It does. An era full of both possibilities and challenges.
Well, on that note, I think we've reached the end of our deep dive, but this is really just the beginning of the conversation.
There's still so much to explore.
So we encourage you to keep thinking about these ideas.
Yeah, challenge your own assumptions about parsimony and complexity. And if you're looking for a place to start, we highly recommend checking out the full paper by Dubova and her colleagues.
It's called Is Occam's Razor Losing Its Edge?
It's a really thought-provoking read.
It might even change the way you see the world.
It might. So until next time, keep diving deep.
And keep those minds open.